Yes, so let's start. Some of you already know Apache Flink or you have even worked with it, but yeah, I wanted to give you a brief introduction. So what is Flink? Flink is, I mean, first of all, it is a top-level project now. We're at the Apache Software Foundation, which means that it is actively developed by, for example, data artisans, but also a growing number of other contributors. And the most important thing of Flink, I think, is its streaming data flow runtime, which actually interprets every program you write, no matter if it's a batch program or a stream program, as a data flow a graph, and basically streams all the data constantly, which is quite different from other solutions out there. And on top of this streaming data flow runtime, we basically have two APIs available. One is the DataSet API, which is mainly used for batch processing. And the other one is the DataStream API, which is for stream processing, as the name says. Yes, we have different programming language choices available. Yeah, Java, Scala, and also now just recently Python for the batch API. On top of these APIs, we have built a number of libraries, which covers, for example, Hadoop MapReduce compatibility layer, which allows you to reuse your, for example, mapper or reduce functions and work with existing data types. And later we will also cover the table API, which is a really cool feature to enable SQL-like queries in Apache Flink. And it's very nice because it integrates very nicely with the other APIs, with the underlying layers you will see later on. And we also have a graph processing library called Jelly, which lets you transform and traverse graphs in a distributed fashion. And a machine learning library, which is very much growing at the moment. We also recently enabled data flow programs to be run on top of Flink. And where this might be exciting in the future when also Google Data Flow becomes more popular. And we are working on cascading, support for cascading on top of Flink. Yeah, for the DataStream API, I think the table API is still a work in progress, but it's almost finished. And yeah, also there we plan to bring data flow and some more. Yes, and you can run your programs written in Apache Flink in kind of different environments locally, which is very useful for debugging, or remote, or even Yarn, or on top of Apache Tez, or in an embedded way. We will see what that means later on. So yeah, I pretty much already said that. I think Apache Flink has some unique features which distinguishes it from other softwares, like, for example, custom memory management and and an optimizer built in, which optimizes your program before executing it. Yeah, but that much for now. There's lots of things to learn about Apache Flink. Oh yeah, I think it's okay you can ask questions freely if you want. Yes, the question was why are we implementing support for Google Data Flow on top of Flink? I would say because there's no standard API language for writing scalable programs yet. So it makes sense that if you have a existing Google Dataflow job, that you can easily run it on top of Flink and use it without, for example, if you own infrastructure, for example, without the Google Cloud. To look at to see a bit why Flink supports all these different use cases like stream batch processing and the libraries, we have to a bit see how Flink can support all these applications natively, and I think that's really different compared to other existing big data software, because, for example, Hadoop has been around for a long time, and a lot of frameworks have been built on top of Hadoop, like, for example, cascading, and they have basically tried to work around the existing capabilities to sort of emulate a behavior, but not really support kind of native execution. And yeah, what does native exactly mean? So, for example, a non-native kind of iteration in a data flow program would be that you have a for loop where you specify the maximum iterations and basically execute a job every time, deploy to the cluster and write to a file, and then repeat this behavior. And that is obviously not a native behavior. And another example in the case of streaming would be to basically discretize a stream into little jobs and execute them one after another, so you kind of have an emulated kind of streaming behavior, but not a native streaming. And that might work for some use cases, but in Flink, this is natively supported, which can be quite useful. So, yeah, also, here are some corner points of the engine again. As I said, everything is executed as streams, and we have native support for iterations in Flink. So we allow, actually, usually in a DAG, in a graph, you don't allow cycles, but we relax this assumption a bit, but in a controlled manner to allow cycles and support iterations natively. And yeah, we have the custom memory manager built in, which tries to prevent out-of-memory errors. And yeah, we have specialized code paths also for batch, so it's not only streaming, although at the bottom layer it's a streaming engine. Okay, so now we will see, after all the abstract talk, a little bit more what you can do with Flink practically. So here we see the stack again, and we have the two APIs built on top of the runtime. Then the first API is the DataSet API, which you can use for batch processing. And basically, what it does is it works around the notion of a dataset, and a dataset is a parallel collection which you can bootstrap from a source, which can be like a file or reading from a database, for example. And then you perform a series of operations which always result in a new dataset. And eventually you define a sink in your program which outputs the data again to some file or database or Kafka or anything. So a very simple example here. It might be maybe too simple for you, but so here we have, for example, a file with a list of triangle data, which consists of a triangle base and height, and so that would be the source. And if we executed this, then we would have the triangles in our data set. We then could apply a map to transform the triangles, each one of them, into rectangles. And afterwards, we could apply a reduce function, which would, for example, sum up all the areas of the rectangles and finally store the area of the rectangles again in a file, for example. So, and the cool thing about this data flow engine is that you can actually set the parallelism in your program, and it basically allows you to scale your program to arbitrary amount of machine and parallel processes. There's no extra work you have to do. And of course, you can also construct much more complicated data flow programs, which consist of multiple sources and sinks, and execute all kinds of different operations and join data sets. We'll see later on how that looks like. So then there's the other API called, which is the Stream API, called DataStream. And it works pretty much very similar, so we will not cover it today, but it's basically also works around this notion of a data stream instead of a data set, and performs a series of operations. It's a bit different, of course, because you have window semantics and different API methods. But yeah, I mean, typical example for that would be like to have a live stock feed with stock prices, and for example, trigger an event, an alert if the Microsoft stock price goes beyond 120, and write that to the database, or sum up all the stocks every 10 seconds and also trigger an alert if the stock prices go too high. Yes, and I already mentioned the data sources. So there are actually many, but the most basic ones which we will work today are the file base, which is a text input format, the CSV input format, and a collection-based sources which allow you to easily create a data source from simple Java objects or collections. And similarly, we have these defined also for the sinks. Of course, you can also use a print output to see what data is generated without writing it to a file. Yes, and I mentioned already that we have a pretty good integration with Hadoop, which most prominently probably means that you can access HDFS, which and also other file systems which are built on top of HDFS. And you can run Flink in a Yarn environment if you want, and not only standalone. And basically, we use the Hadoop data types and input-output formats and functions. Okay, so now I'm going to show you a bit how a program is executed in a Flink cluster. So the basic architecture of Flink is not so difficult, actually. So you have the job manager, which is kind of the master that keeps track of the execution, and a client which deals with the master when submitting jobs, and a series of task managers which also communicate with each other, which are the workers which do the actual computations. So what is the job of the client? The client is, as I said, the entity that submits the job. So the client actually does a series of things. It takes your program, does a type extraction, so it can infer, can actually determine how to work on the types in the cluster, and also check the correctness of your program. And build after the type extraction, we perform optimization to see like how we can generate a data flow most efficiently, and choose the right strategies, for example, for a join operation. And after that, we Flink constructs the data flow graph, which is then passed on to the job manager, where it's being executed. And the job manager, it kind of receives this graph and constructs actually another graph, which we call the execution graph, which is basically just the parallel version of this normal data flow graph. And the job manager then goes ahead and distributes the task to all the task managers and supervises the execution. It handles the failovers in case of any failures, and reports the results back to the client. Yeah, the task managers, which do the actual work, they are consist of a series of task slots, which are basically slots where you can execute tasks that are part of your program. But you don't have to worry about this much, as the job manager deals with filling up these task slots. But it depends on your setup how much you would choose. Usually we choose the number of slots to be the number of CPU cores. And the important thing is that because Flink is a streaming engine, that actually not one slot is filled with one task at a time, but it can be filled with a series of tasks, because data is actually streamed from one operator to another. But in general, all like the parallel instance of your program, like if this would just be the parallel version of your program, then every parallel instance is in one task slot. Yeah, I already mentioned that we have different ways of executing a program. So this is at the bottom of under the runtime. We are here now, and first of all, there's the local execution, which is a very convenient way of executing Flink programs, because it basically starts a Flink cluster locally, and it behaves very much like a distributed setup. Maybe besides that, the actual communication is not going through the network, but it starts all the processes which also exist in the cluster. And it's a very nice way to test your programs. So yeah, you can see all the different processes and tasks run in the same JVM. And then we also have an embedded mode, which is a kind of lightweight way of executing a Flink program. It does not actually start all the task managers, but instead it simply executes everything, all the transformations directly on Java collections, which can be very useful if you have if you work in an embedded environment where you maybe want to perform some quick calculations which don't require like a cluster, and you want to use Flink as well. So, and then there's the remote execution, which is kind of the I guess the kind of execution method you would use if you have a big job and want to execute on the cluster. Yeah, there we run the job manager and the task managers on individual machines of a cluster. And then there's also the Yarn integration, which is currently the best way to run Apache Flink program in a multi-user scenario. Yeah, some of you probably know Yarn. It enables you to do resource sharing, and the way it works is that the client requests containers from the Yarn resource managers, and then starts the Flink cluster on nodes and containers provided by Yarn. Yeah, and actually this is probably the most easiest way to set up Flink or run a Flink program. If you have already an existing Yarn cluster, you don't need to worry with configuration much.
Is there plans for Linux support? And is there like standalone mode?
There is a standalone mode. which is yeah, used to be the default mode before yarn support was added, but the yarn support is now pretty stable. So I think there are no plans currently to add Mesos support, but I'm sure it will come if there's demand for it. Yeah. Yes. We can also execute Flink plans on TAS, which gives you the advantage that you can take advantage of Apache TAS runtime, which is a very good Yarn citizen because it's built with Yarn in mind from the scratch. So if you have a very elastic deployment, you want to add machines or remove machines at runtime, then yeah, TAS execution is the way to go. In general, if you don't have an elastic deployment, then it will be probably slower than Flink. So that concludes the overview. Thank you very much for listening.